Okay, good morning. Very happy to speak here. As you can see, this is a collaborative work between our group and the group of Lincoln Lahoon from Northwestern who grows the wires. And the issue that I'm going to describe here is related to nano-characterizations. One of the main problems of nanowires, in characterizing nanowires, is how to measure and to quantify the dopants inside a nanowire. And what you can see here is the schematics of the most popular way to grow nanowires. This is the VLS method. You start with a gold catalyst, and the wire grows underneath like a mushroom. And what you can see that during the growth, the dopants, the phosphine dopants in this type or N-type wire, go inside both through the sides of the wire and through the top, and it forms a very large gradient of dopants. This is the concentration of phosphorus. Phosphorus is the dopant. So there is a huge gradient mainly across the radius of the wire and also along the nanowire. And what I'm going to discuss in this talk is two issues. First, how to measure the dopant concentration and how to measure their distribution. This is a real problem if you want to make devices out of these nanowires. So the first issue is how to measure dopants in nanowires. For the semiconductor people here, the traditional way to measure dopants in semiconductors is either SIMS or Hall effect. And unfortunately, these cannot be applied yet to single nanowires. So one of the solutions is to use the scanning probe methods. And as you already know, there are many scanning probe methods, electrical modes of scanning probe methods, which can measure electrical properties and maybe dopant concentration. So STM, you all know, scanning gate microscopy, scanning spreading resistance, measuring resistance, measuring capacitance. And the technique that I'm going to use is Kelvin probe force microscopy. But before I go into this technique, I'll explain you why these techniques fail. They work in bulk semiconductors, but they cannot work in nanowires. This is measuring the resistance. This is a technique that Shachar Richter has been using a lot in the past and maybe also uses now, and also Aryeh Ruzin in our department. The problem with this technique is that you need a high pressure to apply a relatively high pressure between the tip and the semiconductor to form an ohmic contact. And it's very difficult to apply to nanowires. This is a paper that just came out now in Nanoletters a few weeks ago, and this show a group tried to measure the resistance of a nanowire with a tip. I will not go into the details, but as you can see, that this is the nanowire. This is the resistance map of the nanowire. You can hardly see any contrast in the nanowire. So this also doesn't work. The scanning capacitance microscopy doesn't work, to make a long story short, is mainly because you need a stable MOS arrangement, a very stable surface or good dielectric between the tip and the sample, and it's very hard to get with a nanowire. So what is one of the solutions? One of the solutions is Kelvin probe force microscopy. As some of you know, I've been using this technique for almost more than 10 years now. This is a very simple way to measure the potential difference or the work function difference between a tip and a sample. The main advantage of this technique is that you have a zero applied field or no tip-induced bias between the tip and the sample. The disadvantage of this technique is the resolution. The resolution of this technique is on the order of 10 or 20 nanometers because the electrostatic forces that develop between the tip and the sample are long range. So the resolution is not so good, but this is a very quantitative technique and gives you an absolute value of the work function difference. And if you calibrate your tip and the work function of the tip is known, you can get very nice results, as you will see in a second. So just to start with an appetizer, I'll just show you that the Kelvin probe can be used as a very simple and elegant four-point probe. One of the ways to measure the resistance of a wire is to put 4 electrodes across a wire. This is the wire. And to measure with a 4-point probe the resistivity of the wire. If you use Kelvin probe, you can do it only with 2 contacts. What you see here is the topography of a typical nanowire, and this is the potential measurement using the Kelvin probe. And if I look along this line, this is the scan of the potential. And if you have the potential profile from the potential, you can get the electric field. And if you measure the current between the two contacts, you have the current, you have the electric field, and you can get the dopant concentration. So this is a simple way how to use Kelvin probe force microscope only with two contacts. But this is just, I'll show you what we use it for further on. If we measure the potential drop along a nanowire, so here we have the two contacts, and here we have the gold catalyst of a silicon nanowire. And if we measure the potential drop along the wire, if the dopant concentration is homogeneous, the electric field will be constant along the wire, and we'll have a straight line of the potential here. But if we measure such a device, what we find, this is how the device looks under the SEM, and we take it into our glove box to measure the KPFM potential profile. If we measure the potential profiles along the wire, if you look closely, you can see that the potential lines are curved. That means this, if you see this curvature here and here, this means that the electric field is not constant, and you have a dopant gradient along the wire. And the end result of this analysis is that you have a dopant gradient along the wire. It's not so severe. It's a factor of 2, as you can see, between 1 times 10 to the 19 and 2 times 10 to the 19 across about 10 microns. So this is not a severe problem. The more severe problem is the radial dopant distribution. Again, this is the wire, and what I'm going to show now in the main part of the talk is the very inhomogeneous dopant distribution along this axis. What I've shown until now, very shortly, is this gradient is only a factor of 2. So this is not a severe problem. So how to measure the dopant concentration in the radial direction? So we came out with a very nice idea. We start with a wire. We start with a wire, and we start successively etching it. So we put a mask, and then we open a window in the mask by etching, and then etch a portion of the nanowire. We form a step here. Now, if the dopant concentration along the wires is not constant, this will give you a potential step because the charge concentration is not constant. So we come with the AFM tip or with the KPFM tip and measure this step. And if we repeat this process several times, we can measure the dopant concentration along the radius of the wire. So we repeat this process several times, put another mask, and this is all done with the electron beam, do another etch, and then forms a series of steps. And if we measure it with a Kelvin probe force microscope, what we will actually measure is this profile here. This is the Fermi level, which is constant, and going from right to left, we will measure this profile here because the wire is more heavily doped in the circumference, and as you go into the wire, it's less and less doped because of diffusion, if the diffusion of dopants is strong. And you will see this in a measurement in the next slide. So this is just after one etch, just to show you that the resistance of the wire changes. This is after one etch. One problem is that the etching doesn't give a very smooth surface. And then if you do several etches, we can measure it with the SEM. You can see we zoom in. This is one of the steps, and on this wire, you cannot see it, but we have 4 or 5 etching steps. And now we measure it both in topography and in the KPFM. So this is the topography map of the steps, and this is the potential map across these steps from left to right. And basically, it resembles more or less the change of what we actually measure with the Kelvin probe is the change of the local vacuum level, which follows, if there is no change in the electron affinity, which follows the conduction band minimum. And this, by analysis, this will give you the dopant distribution. So the dopant distribution, if we do the analysis that I will show you in a moment, this is not the dopant distribution yet, this is the surface potential. And now, from the surface potential, we have to solve the Poisson equation to get the dopant distribution. But before that, since we had a feeling that we have a very inhomogeneous dopant distribution, because people from semiconductor physics know that if a potential drops by several tens of millivolts, there is a 1 order of change in the dopant concentration. So this, you have a potential drop of 70 or 80 millivolts from across 25 microns. This means that the dopant concentration drops by almost 2 orders of magnitude. So this means that we have a very strong diffusion here. So we solved the diffusion equation. I don't have to describe it now. Ignore this equation. Just this is the equation we use for solving the diffusion problem in cylindrical coordinates. And what you see here is calculated surface potential profiles, 4 profiles. And this is our measured surface potential. So what you see that for a diffusion constant of dopants of 1 times 10 to the minus 19 in units of meters squared per second, we have not a very good fit, but a very good fit only in the beginning, or in the outer part of the wire, and here not a very good fit, and I will come back to this in a moment. But qualitatively, we can come out with a very large diffusion constant of dopants in this direction. Now, how do we calculate the surface potential? We solve. I will not elaborate it. We're solving the three-dimensional Poisson equation, and what we get is this donor concentration, and we use this. We plug this donor concentration back into the diffusion equation, and get back this profile. This is how we do it. So we have a very strong diffusion. And what this implies, if we have such a very strong diffusion of dopants, here I plot the dopants concentration across a wire. So the solid line is the donor concentration from one side of the wire to the other. So you see a drop of almost 2 orders of magnitude. And if we calculate the current between source and drain of such a device, you will see that the current, this is a cross-section of the current density. You see that the current flows mainly in the outer part of the wire, and this is understandable due to this huge dopant gradient. So this is a simulation of the current for a certain source-drain bias. Just to solve the issue, to get a better fit, if we want to get a better fit between the measured surface potential, these are these error bars, and the diffusion, we added the effect of surface states, and if we add surface charge in the outer part of the wire, we get a much better fit also in the small radiuses of the wire. And you see that again with a diffusion constant of this magnitude, 1 times 10 to the minus 19 meters squared per second, and with a surface state density of 5 times 10 to the 11, we get a fairly good fit through the whole range. Now, what this all means? This all means that for nanowires, this is the diffusion of phosphorus in nanowire. This is the diffusion constant that we obtain, and this growth temperature of about 500 degrees. We have much larger diffusion constant than obtained in bulk silicon. All these data are from the literature for diffusion of phosphorus in bulk silicon. So what we have found here for the first time, and nobody to our knowledge have measured the diffusion constant in nanowires, that the diffusion constant is at least 1 order of magnitude larger than in bulk silicon. So if people want to make devices from these nanowires, they have to solve this problem. This probably can be solved by annealing, and we are working on this right now. In the last few minutes, I would like to describe you a new set of experiments, how we think we can use the Kelvin probe force microscope to find individual electronic traps in a nanowire. What you see here is an intrinsic silicon nanowire, undoped nanowire between source and drain. And what you see here is potential scans for different applied gate voltages. These are negative applied bottom gate voltages, and these are positively applied gate voltages. And you can see that for a negative gate voltage, we don't see any structure in the wires. But when we start applying from, let's say, minus 0.5 volts and going more in a positive direction, we're starting to see bumps in the nanowires. These potential bumps are due to change in the potential, in the energy difference between the Fermi level in one of the bands. And you can see it happens only in a positive bias. So what is actually happening here, that we are populating or depopulating trap states inside the nanowires. Here you can see the image, the KPFM image for a gate voltage of 1 volt, and you see that the topography image is featureless. So there's no crosstalk problem here. Now, if we do some simulation, we solved the Poisson equations, and we put either acceptor type traps or donor type traps, and you can see that when we put an acceptor type trap at a certain energy that I will soon show, we see a feature that resembles our measurement for a negative applied bias. And this is this is the bottom line. I will go backwards now. So what I'm going to show you in this short animation is the following. We have the wire. This is the nanowire. This is how the experiment is done. And we apply gate voltage from the bottom. And as we apply the gate voltage, you will see soon that the Fermi level is moving. And we have done simulations. We've done simulation by changing the gate bias and watching the relationship between the Fermi level and several trap energies. Now, as the trap energy changes, the population of the trap as a function of the applied gate bias will change. So, for example, this is for a gate bias of minus 1 volt. Now, if we applied this voltage, the Fermi level goes above this trap, and this trap is populated, and we will start to see a change in the peak that we measure. So this is the measurement. This is the peak height. By peak height, I mean, I'll show you again. I don't want to go back. The peak height is the height of these peaks, and this is the applied gate voltage, and this is the calculated peak heights for different trap energies. So, and if we go further, we have to go backwards. So we change the gate bias, we go to minus 0.25, then there is another population and trap, and so on. And the basic idea is we want to try to get a fit between the measurements. This is the measurements, the average of many peaks, and these are simulations for different location of traps. So this study is not complete yet, but what we think that the traps that we are seeing are for about this energy, and they are very close to the wire surface, right at the surface of the wire, by the peaks that I meant these peaks height. Okay, this is it. So what I've shown you is few things. First, that KPFM can be used to obtain quantitative dopant concentration in silicon nanowires, both the concentration and the distribution of the dopants. We have seen that the dopant concentration decreases by a factor of 2 along the wire, so this is not a severe phenomena. So a factor of 2 for 10 microns length. But in the radial direction, across the radius of the nanowire, there is a huge drop in concentration, almost 2 orders of magnitude along 20 or 30 nanometers. So this implies that if we want to use such wires for devices, we must anneal them or get rid of this phenomena. And in the last part of the talk, I've shown you that we may be seeing bulk traps, and we may be able, due to the gold atoms that come from the gold catalyst, and we may be able to identify the energy in maybe the concentration of these traps. By the way, we can get the concentration, just to give you an idea, since I have 1 more minute. We can get the concentration by the distance between the peaks, and we can estimate the concentration of about 10 to the 15 or 10 to the 16 traps per cubic centimeter. Okay, this is it. I want to again thank my students and my group. All the experimental work in this study was done by Elad Koren, who unfortunately couldn't come to the conference. And all the wires were grown in the group of Lincoln Lahun in Northwestern. And I thank you, of course, for your attention.
Yossi, thank you very much for going to talk. Now we have plenty of questions.
Were the nanowires grown by co-depositing silicon and phosphine, or were they first grown with silicon and then doped with phosphine?
Together.
Then why is it appropriate to talk about the diffusion coefficient? They should have, in principle, it all should have been uniform.
No, but the silicon goes only through the top, through the gold catalyst, and the dopants go through the sides.
How is that known?
This is by the method. I'm not expert in this, but this is the principle of the VLS method. But there is a eutectic reaction between the gold and the silicon, so the silicon grows only like a mushroom from the top.
Thank you.
You described unhomogeneous radial concentration as a problem. Why is it a problem?
Well, depends for what. You're right. If you want to make it like a transistor from this, if let's say. Depends on you're right, on the device that you want to fabricate. If you want it to be an homogeneous part of a p-n junction, so this wire will be an n-type side of a p-n junction, then you want it homogeneous. But if you want it to be, let's say, that you want it to be, this is a very good point, you want it to be a part, let's say, of a solar cell, and you want the solar cell to have this potential profile, then it's not a problem. So you're right, for certain applications it's a problem, for certain maybe not.
Yossi, you've shown the response of the transistor characteristics of these devices before and after etching.
Yeah.
And it seems that the device has no gate dependence before etching and a very strong gate dependence after etching.
Yeah, this is because the change in the dopant concentration. After etching. After you etch, you mean this. So before etching, this is before etch, it has shows an ohmic behavior because it's very highly doped on the surface, 10 to the 20th almost. And after you etch a few nanometers, it shows a transistor behavior because it's more lightly doped. This is the effect. And several groups have seen this. So before you etch it, it's completely ohmic. Doesn't show any reaction to the gate bias.
So you really need to get rid
of this high, very high surface dopant concentration.
Yossi, in principle, I know you demonstrated very nicely a measurement of a single wire, but in this case, at least for comparison, you could have taken many wires together and do a secondary ion mass spectrometry as a comparison, or even other chemical analysis.
But then you measure the average. People have no, I don't know if people have done it, but people wanted to know if you average, then you lose the so I don't know if people have measured they've measured by seams the average concentration, but by seams you cannot do this radial distribution by seam, not very, and seams also inserts a lot of damage. The profiling by the seams in 20 or 30 nanometer diameter wire is a problem. But you're right. If you want to measure with the seams, you can measure many wires together.
When you said you use the diffusion equation, did you mean the simple diffusion equation or diffusion under external?
Simple diffusion equation we took from the literature. What electric field? You mean the internal field of and you think it can affect the diffusion? The diffusion of the dopants? We're talking about diffusion of the dopants, not diffusion of the carriers. So I don't know if this is a strong effect. In this equation, we didn't use any external field. But we're talking about diffusion of the dopants. I don't think they're, well, we can check.
Just during the growth, right? It's not when you apply the electric.
No. During the growth.
And this is just diffusion.
In cylindrical coordinates, no. In a cylinder covered by these cylindrical dopants configured. Yeah. We take this into account also. The time, we take this into account also. Well, we as some people, this is right. Some people have done it like this. After growth. There was a paper even in Nature Nanotechnology, but they've also found a very inhomogeneous dopant profile. You're right, but the issue is that you have to grow the wire in this gold silicon eutectic temperature of 500 degrees C, and this is the most common method, and people find that the object of our work was to find what is the diffusion gradient. I'm not saying that it cannot be overcome. But yeah. But okay, you are right. But people wanted to dope the wires during the growth. But you're right. Your point is a valid point.
Okay, let's